Hello, everybody. So what this video is the week 5 lecture 1 video. And what this is going to cover is some of what you will see in those iBooks for chapter 5. So if you look at chapter 5 in his iBooks, the first thing that you'll see is the Java example for salary calculation. This is essentially identical to a lab that you've already done. And so you can take a look at it and go through it. It is actually not worth points because if I open it up, you'll see that it's not labeled as a challenge activity or a participation activity. And then you have a couple other sections here. So this is a pretty short week. You should be able to get through this without too much trouble. Nevertheless, actually, some of this, like the binary stuff, is a little bit trickier than you might think. And so I will explain that. And coming back to the class, you'll see that we have a set of, what's it called? Lecture slides to look at. It also says modulo operator. I realized that's what it said last week, and I forgot to delete it because I copied the section from there. So we're not actually doing the modulo operator today. We did that last week. But we do need to download this PDF here. So let's do that. And we're going to go over these lecture slides. Okay, so what are we doing? So what's in here is typecasting, first of all, with doubles and ints. We'll need to look at Eclipse a little bit. So let's just go ahead and open up Eclipse. Can't spell words. Eclipse. Oh, it was open already. And I'll just delete whatever's in this file, this current one. It will not be the mod example. All right. So typecasting, which we're going to talk about soon, binary numbers, which is decimal to binary and binary to decimal both ways. And then we have characters in Java. Characters are like letters or symbols on the keyboard. Now, it's likely that I will not be able to do characters and strings in this video without it going over an hour. So we'll at least try to do typecasting and binary numbers, at least to some extent in this video. So let's just go ahead and get started. So what typecasting allows us to do in any programming language, but Java in particular, is that it allows us to convert variables from one data type to another data type. And in Java, where that's going to happen most often is between doubles and ints. Now, why would that be the case? Well, doubles, as we know, can store decimal values, fractions, and integers can only store whole numbers. And so a common case where that could happen is when you're doing something like averaging numbers or anything like that. So I'll show you an example over here in Eclipse. So I'll come here and will create a couple of variables. So I'm just going to say like, I don't know. I think the example they use in the Zybooks is like a number of kids. So let's say like num kids 1. And let's just put a number of kids there. Like I feel like 5's a lot of kids. Um, int num kids 2. Put a number there. Let's say 2. Okay. So we have number of kids 1 is 3, number of kids 2 is 2. So there's 5 kids total, okay? Now, if I wanted to calculate the average number of kids, right, I could say double average kids. Um, then we could try to calculate how many kids on average we have here. Maybe we'll add a couple more, actually. I'm kind of feeling like we should. So we'll have like num kids 3. Let's say that they also have 2 kids. And what do we have? 1, will that work? No, that won't work. Okay, so let's do this. So these are going to be the number of kids that like 4 families have. Let's say 4 families number of kids. Okay. Um, and so what we got going on here is they got 3 kids, 2 kids, 3 kids, 1 kid. Got an error here because I haven't done this. So if you wanted to calculate the average number of kids that like this family had, what you would have to do to calculate the average is you'd have to add up the number of kids, right? So you'd have to add up the first number of kids plus the second number of kids plus the third number of kids plus the fourth number of kids, right? Make it smaller. You'd have to do all that. And then after you did that, what you'd have to do is divide by the total number of kids, or sorry, the total number of families, which in this case was 4, right? And when you do that, you're going to get a number and you could print it out. So let's do system.out.println and we'll just print out average number of kids and we'll put the average kids there. Okay. Now, when I do this, I get that the average number of kids is 2.0. Okay. But is that right? Because if I grab a calculator, let's grab a calculator. If I were to work this out, I've got 3 kids plus 2 kids plus 3 kids plus 1 kid, which adds up to 9 kids total. And if I divide by the 4 families, I actually get 2.25. So the average number of kids is actually 2.25. But what we see here is 2.0. And the reason that we get 2 there, right? We get 2.0 from this calculation, which is wrong. Because why? Well, we should already know from when we were learning about integers from the previous week. So the problem is that Java will see that we're adding up these 4 things. They're all integers. So the top here is an integer. And then we're dividing by 4, which is also an integer. And when you divide an integer by an integer, you get an integer, right? So we get 2.0 because it does the essentially 9 divided by 4 as a integer divided by integer calculation. So we get no decimals, right? So we get a whole number, which is an integer. Now, we were storing the number in a double. So it still looks like a regular, decimal number, but the calculation was still done wrong because it evaluates the right-hand side first to get to blah, blah, blah. It evaluates the right-hand side first to get 2, and then it stores that 2 as a double, and that turns it into 2.0. Now you could fix that. So we can fix that uh, simply just by writing the 4 as 4.0. Because as soon as you put a introduce, sorry, can't do 2 things at once. As soon as you introduce a decimal to the calculation, then Java will say, oh, we must be actually dealing with a double, we need fractions. So what I mean by that is if I change this to 4.0 like that, and we run this again, you'll see that the first calculation is 2, but the second calculation comes up 2.25, which is correct. And so just changing that 4 to a 4.0 just magically fixes that. So you might think like, okay, we'll just do that. Whenever we have doubles, we'll just make sure that we type them as 4.0, 2.0, whatever we're typing in. and that will solve all our problems. But it doesn't solve all of our problems because what if instead of the 4, we also had a variable for the number of families? So if I went up here and I said int num families, and I made that 4, so now this is an integer as well, and I tried to do this again, but so this will be wrong again due to int over int. If I replace this 4 with that num num families like that, then now we're back to the same issue because we still have integers on the top and integers on the bottom. And there's no way to fix it by writing point oh anywhere, right? Because there's actually no numbers written on this line, right? Line 26 has no numbers. So you can't just fix it the way that we fixed it last time. And so the only solution is, we could fix this again using type casting. Okay, so what typecasting does, flipping back over to the slides, oops, wherever they are, they're in the preview app, which is here. Um, so what the typecasting allows us to do is to treat a variable of one type as if it was another type. So basically we can force it to convert the way that we want it to. So what does that mean? I don't actually see a good example there. Um, so I'll just show you in Eclipse. So what you could do is this. So basically what you do is if you want to treat the top or the bottom as a double, you just in parentheses, put parentheses and then write double like that. And you'll see that it color codes it. And what it'll do is whatever you put this next to, whatever's immediately to the right, will be treated as a double. And oh, I shouldn't have done that there though. Let me just repeat this so I can copy paste it. So we want to treat the top or bottom as a double. That's what we want. So how do we do it? Either at the beginning of the line, you can put double, in which case it will turn whatever is to the right into a double. And that will be the right answer. Or if you put the doubled over here next to the number of families like that, that's basically going to turn the number of families, which is 4, into a double, make it 4.0. And so really, if we do it this way, essentially what we've done is we've made this line 34, look basically like this to the computer. To us, it looks different. But when it's 4, that's a problem. When it's 4.0, that's good. Well, here it's variables, but num families is 4 and double num families is 4.0. So it's the same fix. Now, something you'll see as well, if you look in the section of the book, is that they will take this double and they'll put it on here and here. So they'll say the top is a double and the bottom is a double. Now that's perfectly fine to do. You'll get the right answer. It's not strictly necessary though, but you can do it. So we can treat anything we want as a double. Now, you can also do that the other way around. You can treat things as integers if you want. So, for example, if I say just like double, I'll say pi, and we'll just say 3.1415. That's not exactly pi, but close enough for right now. Now, of course, if I print this, right, system dot out dot print line, and I go pi, um, like this. Maybe I'll go pi. Well, then of course we're going to get that 3.1415, right? There it is, pi, 3.1415. Now, just to show you what you can do with typecasting, like what if I just write int right there? Then I would be saying treat pi like an integer. And you just get 3. Okay. So you don't have to turn integers into doubles. You can turn doubles into integers. And so you just want to be thinking of what these variables are used for. And, in rare occurrences, you may need to typecast. So again, the way you do that is simply by um, you simply put in parentheses the type that you want to turn it into. So here pi is a double, but I write int next to it, and now it's an integer. Simple as that. Now, just to show you what's in the Zybooks for this, we'll go there, type conversions. So they'll explain all this. They'll also explain that this can happen automatically. So like if I do, well, this is kind of silly, but like it's not pi anymore, but like if I put 5 there, um, 5 is an integer, right? And pi is a double. Um, but there were no issues here because an integer can be turned into a double without any trouble. The other way around can't happen though. So like if I do, like let me just change this to like x or something because it's not pi anymore. Um, so you can, I'm gonna get an error because of that right there. So it's not pi, but so if you say double x equals 5, that's fine, even though the right-hand side is an integer. The other way around doesn't work though. So like if I say int y equals 5.0, this is an error. So here the right side is a double and the left side is an integer, and you can see that it's complaining already. Whereas on the previous line, the right side is an integer and the left side is a double, the other way around, and there's no issues. So what's happening here is that 5 can be turned into a double basically automatically. 5.0 can't be turned into an int. And in both of these cases, it's more that we're talking about automatically because we know that, of course, you can we know that you actually can turn 5.0 into an integer because we get an error here, but I know that if I just go here and I do that typecasting that we just learned how to do, that would fix my issues and everything runs. So you can't turn an integer into a double automatically. You have to typecast. Okay. So over here in the exercises, they're talking about that. And so if it happens automatically, they call it implicit conversion. So like the computer had to convert it for you, but it didn't even bother to tell you. It was just going to do it automatically. Um, Now, if we think about what we know about types, you should be able to work these out. So, pay attention to what's a double and what is an integer. So if you were to do 3.0 over 1.5, you should understand that since these are both doubles, we would get 2.0, not 2.0, right? So we do. If you do 3.0 over 2, as long as there's a double involved, which there is, the 3.0, then it would work the same. So you get 1.5, that'd be fine. Now they told us that right here that num items is 5 and also it's an int, right? So what's happening here is num items plus 10 is 15. 15 divided by 2 is 7.5. 7.5. But everything's an integer here, right? So everything's an integer. So when you do 15 divided by 2, you do not get 7.5. You just get 7. Okay? Everything's an integer. Now, when you change the bottom to a 2.0, we saw this just a few minutes ago, that will force it to do the double arithmetic, the floating point arithmetic, And now it'll do the calculation correctly and give you a 7.5. So this is all just what we talked about. But you can check your results. Here they explain the typecasting. If we scroll down, you'll see them doing it. This was kids in the family, so this is like exactly what we just did. Notice that to typecast, they just write double in parentheses next to whatever it is they want to turn into a double. This should also not be on separate lines here. Like this code would not compile. Okay. So determine the resulting type. So everything, all the variables are integers. So we're only going to get doubles if we typecast or if somebody types like a 0.0 type thing. So if you think about this first one, integer, 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 everything's an integer, so it's an integer. Now here, as soon as you put a double on it, we have a double involved. That's going to turn the whole thing into a double. Here, this is integer, integer, integer. So this is an integer. And here we have integer, integer, and oh, look, this one's typecast. As soon as you typecast it, you're going to get a double. Okay? Um, they say common error would be forgetting to cast your results. So this was an example of just everything had integers except the average kids per family. And they did the calculation without typecasting and they got the wrong answer. But that's the exact example that we used, right? So fixing this would involve putting just a typecast of double either here in the numerator or here in the denominator or both. So if we go down here, we got some activities. Let's do a couple at the bottom. I'm going to skip this one, I guess. This is similar to the participation activities we've already done, I think. So let's do 5.2.2. So it says integer numFeet is read from input. There it is, I see it. Complete the output statement to typecast numFeet to a double. Oh, okay. So they just want to print the number. So the number is numFeet, and they told us to typecast it, but I'm not going to yet. I'm just going to hit check and get the wrong answer. Okay. So let's let it do its thing. You'll see that I output 17, but I was supposed to output 17.0. And that's because I did not typecast like they said to. So how do you typecast numFeet to a double? Well, you just go to the left of numFeet and in parentheses, type double. Usually you would leave a space. And that'll fix it right there. And there we go. Let's jump to number 3. This looks like what we have just done. So let's see. Integers, numkids A, numkids B, numkids C. Okay. Num groups. So we have 3 kids and then the number of groups. So like the number of groups would be like 3, right? Because there's 3 of them. Compute the average kids per group using floating point division and assign the result to average groups. So the variable is average groups. The way you calculate an average is by adding up all the things and then dividing by how many things there are. So we have numkids A plus numkids B plus numkids C. That's the numerator. And then we have to divide by, there's 3 groups, but we're supposed to use the variable num groups. And if this is what I did, I would get the wrong answer. I would get the wrong answer because everything here is an integer. So in order to fix it, they want us to typecast. We need to realize that since our variables are all integers, but our answer is going to be expected to be, a double, have fractions involved, decimals, we need to typecast, right? This is not really optional. We'll get the wrong answer if we don't typecast to a double. And you can typecast just in the numerator or numerator and denominator, and that'll be fine. So this will do it. So you have to know how to calculate an average, and then you have to know how to typecast to a double in this case. There we go. And we got it. So they checked it out and, we did indeed get decimal values. So that's typecasting. We can do some of these as well if we want to. This is just going to be checking if we understand ints and doubles. So like number is 1, new number is number times 4. So that's 1 times 4, which is 4. Everything's an integer, so we're printing it out. It'll be a 4, and I see it's a print line, which means we have to hit enter. Check. Let's jump to number 3. Now we got doubles. So number is 4.0. New number is number, which is 4.0 times 3. 4.0 times 3 is 12. But both of these are doubles, so it's not going to store 12, it's going to store 12.0. And again, this is a system.out print line, so we'll hit enter. I didn't do number 2. Let's do number 5. Jump to the end. Oh, okay. So this is very, very similar to the ones that we've done already. Get a calculator in case the math is hard. So we're going to be printing out system.out print line double kids in class 1 plus kids in class 2. So that's 2 plus 3, right? So we'll have 2 plus 3 will be 5 divided by, we're dividing by num classes, which is a 2. So we're doing 5 divided by 2, okay? And this is got casted as a double and casted as a double. So when we run this and we get 2.5, everything was casted as a double, so we will get 2.5 as our answer. So the first thing printed will be 2.5. Now, if you look at the bottom print statement, it's kids in class 1, which is 2, kids in class 2, which is 3. So that's 5 when you add it. Divide by 2, you get 2.5, but they did not cast to doubles, which means that this was 5 over 2 as an integer arithmetic. And we know that you lose the decimal place, like it does it as an integer calculation, you lose everything on the other side of the decimal point. So it's just going to be 2. So the first one is done properly with typecasting, and the second one is done wrongly with no typecasting. Okay? And so you just have to know that this exists so that, first of all, when you have a bug in your code and you don't know why, you can think about typecasting as a possible issue. And also, you can do it right the first time and not make the mistake in the first place. Okay. So that is typecasting. So then we want to move on and we want to talk about binary numbers. Now, this is a bit tricky here because with binary numbers, it's easier to write them by hand than it is to type them or do them on a computer. And I don't have my iPad hooked up right now. This is on my laptop. So I'll just have to type things here. Now, you can go through this yourself, of course, but I will try to do it. I'll go over here to, I guess, Visual Studio Code. So I'll just type some stuff. Okay. So when we're talking about binary numbers, first of all, we should know what decimal is. So when we talk about decimal numbers, right, that means base 10, which is our kind of our normal numbers. Okay. So decimal numbers, base 10, those are our normal numbers that we always use. And when we're talking about binary numbers, these are what base 2 numbers are, and these are what your computer uses. What computers use internally. So specifically, what do I want to say? Specifically, binary numbers are how everything is going to be represented in the computer. And I mean everything, right? So every, integer, every character, every string, every floating point number, everything has to be a binary number. It's only going to use zeros and ones. So let's just, before we do this, talk a little bit about decimal numbers, base 10, right? So what do I want to say about base 10? Well, first of all, these are our normal numbers, right? These are our normal numbers. So, like, for example, if I say 375, right, is a normal base 10 number, right? That's what we're used to. Now, if you do write something like 375, what does that mean? Well, of course, you've been working with base 10 numbers all your life, and so you have no issue thinking of the number 375 and understanding what you mean. But you could understand that 375, that each number in each place has a specific place. So, like the five, we would say is in the ones place, right? Five is in the ones place, right? We have the seven. Seven is in the tens place, right? And we have the three. Three is in the hundreds place, right? And so, see if I can move these over a little bit. That. So we have five is in the ones place, seven is in the tens place, three is in the hundreds place. What that means is that if we took this all together, that 375 technically means that you have 375 is equal to, well, the five in the ones place means 375 is five times one. I'll write it just like this. So 5 times 1, because 5 is in the ones place. But then we have 7 in the tens place. So that'd be 7 times 10. And then you have 3 in the hundreds place, 3 in the hundreds place. So that would be 3 times 100. And hopefully this makes some kind of sense to you, right? That 375 is 5 times 1, 7 times 10, and 3 times 100. Okay? And it's 1, 10, and 100 because we are in base 10. And so the 1 is actually 10 to the 0 power, and the 10 is actually 10 to the first power, and the 100 is 10 to the second power. Now, I don't know if I can type superscript here to do the exponents, but I could write it this way. 375 equals 5, and then the 1 is 10 to the 0 this way. Hopefully you understand that kind of writing. And then 7 times 10 to the 1, and then 3 times 10 to the 2. And so 10 to the 0 is 1, and 10 to the 1 is 10, and 10 to the 2 is 100. Okay? And so that's really just kind of a short explanation of what it means to be like a decimal number, right? Every digit has a place, like the ones place, tens place, hundreds place, and they mean something. Okay. Now, if we have to come back up here and type more in the decimal later, we will. But let's see if we can think about what this would mean as far as binary numbers go, which would be base 2. All right. So these are our computer numbers. The digits are only going to be 1 and 0. Those are the only digits that you'll see in a binary number. Now, I didn't say it up here for decimal numbers, but decimal numbers are base 10. And so you see the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 in base 10. And if you count these up, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, there's actually 10 of them, right? The biggest one is 9, but since we also have 0 on the end, there's actually 10 of these numbers. So the fact that we have base 10 means there's 10 digits involved, and these are them. Now, the fact that base 2, uh, well, the fact that base 2 is what we're looking at now, binary base 2, we're going to have two digits involved, just 0 and 1, right? So only 0 and 1 rather than 0, 1, 2, 3, 4, etc. Okay, so binary numbers, the computer numbers, digits are only 0 and 1. What else you say about them? There was something. I can't think of what I was about to say, but what? Yeah, I can't think of what I was about to say. I'll say something else. So the digits are only zeros and ones. So a number might look like this. Probably put an extra one there or something. So this would be like a number in binary might look something like that. So you're not going to see anything other than ones and zeros. Okay. Now you can have any combination of ones and zeros, and it can be as long as you want or as short as you want, but they're going to look something like that. I remembered what I was about to say now. I was going to say a single one or zero is called a bit. Eight of those together, eight, one, or zeros is a byte. So for example, 1 byte could be, this is just an example of 1 byte. We just need 8 digits. So like 1001, maybe, 0110. That's eight, right? So we have eight of them there. That's a byte. So 8 bits is a byte. Okay. Now, the thing is that because all these numbers in the computer are represented in binary, we need to be able to write our normal numbers in binary or our binary numbers as normal numbers. So we need to be able to convert binary to decimal and decimal to binary, right? And that's what we're kind of going to learn in this section. Now, like I said, this is easier to do when you have, like, when I have something to write on, but we can still do it this way. So one direction is easy and one direction is hard. So if I'm trying to convert a number from binary to decimal, this is the easier direction. So binary to decimal, this is easier to do. Um, and so we basically just do exactly what we did here. Here. So when we say like 375 is 5 times 1 plus 7 times 10 plus 3 times 100, you can do that same exact thing, but instead of using 10 to the 0, 10 to the 1, 10 to the 2, right? 1, 10, 100, 1,000, etc., we're going to use powers of 2. So when you're doing binary, you need powers of 2 instead of powers of 10. So this will look just like this example, except we'll use powers of 2 instead of powers of 10. Okay? And so what would that look like? Well, we need a number to try to convert. Like you can't really just explain this in words and have it make sense. We need like an entire number. So let's pick an example here. Example, convert, we just need a number. Let's say 1011, 10, yeah, okay, 1011. That'll be our first one. Um, I want to do more digits. Okay, we're doing this. 101101. Big number. Okay. Um, from binary, which is base 2, to decimal, which is base 10. Okay, so that's the example that we're going to try to do. Now, what we have here, I'm looking at that number and I just realized that there's something I don't like. The something that I don't like is it was symmetric left and right, and that might confuse people who are like trying to figure out like did we start on the left side or did we start on the right side? So I just changed it to 101011, and we want to convert that from base 2 to base 10. How? Well, let's start with our number, right? So our number is 1011101011. Okay. Now, what we want to do is the exact equivalent of what we did up here. But remember that this one here was actually 10 to the 0, and the 10 here was actually 10 to the 1, and the 100 here was actually 10 to the 2. That's very important, okay? And also notice that we started with the 5 and then the 7 and then the 3, which means we started at the ones digit and the tens digit and then the hundreds digit as we moved to the right, or sorry, to the left. We started on the right-hand side. Same thing is what we have to do here. Now, what does that mean? What that means is you have to take the first digit, which is a 1, and you need to multiply it by, well, what place is it in? Well, the place that it's in is the ones place. So we start out the same way as we did up here, right? So this was 5, and it was in the ones place. So it's 5 times 1. Well, this is a 1, and it's in the ones place. So it's 1 times 1. Now, the next digit up here, the next digit was 7, and it's in the tens place, right? Well, here the next digit is a 1. It's not in the tens place, it's in the twos place. So instead of going 1, 10, 100, you have to go from 1 to 2 to 4 to 8. So powers of 2. So the second one here is in the twos place. Okay. Then the next digit, the third digit, you can make that easy, bigger without. I wish it could be bigger and still we could fit a lot on the screen, but we can't really. So you have 1, 1. So we have the 1 and then the 1. And then the next digit is a 0. So we would have a 0, and that's the fours place. So 1 times 2 is 2 times 2 is 4. The next digit is a 1, and that is the eights place. And then the next digit is a 0, and that must be the 16s place. And then the last digit is a 1, and that's in the 32s place. And so you could do that. Now, I explained all that and I wrote it all down. Another way to do it, I'm going to erase it and just type it the same exact thing, so don't worry. Another way to do it would be like, what if we just wrote these numbers, but like backwards? So like we have 101011, so we end with 1 1. If I wrote it backwards, it'd be 1 1 0 1 0 1, like this. And then I'm just kind of spreading them out. So I'm just spreading them out. And then basically on the first one, you put a 1. And then on the second one, you put a 2. And the next one, you put a 4. Next one, put an 8. Next one, you put a 16. Next one, you put a 32. So 1 times 1 plus 1 times 2 plus 0 times 4 plus 1 times 8 plus 0 times 16 plus 1 times 32. That is essentially what you have to do here. So it's the same thing up here as 1, 10, 100, but it's 1, 2, 4, 8, 16, 32. Powers of powers of 2. Now, you do all that, but what does that mean? Well, it means literally just add up those numbers now. So what I mean by that is we have, I forgot to do that. What we have here is 1 times 1, which is 1. And then you have 1 times 2, which is 2. And then you have 0 times 4, which is 0. And then you have 1 times 8, which is 8. And then you have 0 times 16, which is 0. And then you have 1 times 32, which is 32. And then if you add up these numbers, what are you going to get? Well, 1 plus 2 is 3, plus 8 is 11, plus 32 is 43. Is that 43? I think. So I'll do it this way. 32 plus 8 is 40. 40 plus 2 is 42. Plus 1 is 43. So there we go. Now, you have to understand what the equal sign means, right? On the right side, that's base 2, and we converted it to be base 10. Okay, let's go over to the Zybooks and see what we have in there regarding this to see what we can do. So they're going to explain this. Look, you can see that they used powers of 10s just like we did. Then they're saying that this number uses powers of 2 just like we did. And they give us this tool here. So you notice the numbers go 1, 2, 4, 8, 16, 32, 64, 128, right? This is just what we did. Now we only had how many digits? We had 1, 2, 3, 4, 5, 6, right? If you count up the digits in that number, there's 6. And so over here, 1, 2, 3, 4, 5, 6, we only went up to 32, right? We didn't have a bigger number, so we didn't need these bigger ones. Now, what this is useful for here is that the math that we just did, you kind of don't need, because when they say convert the binary number 00001111 to a decimal number, we could do exactly what we just did, but they are giving us this tool here that we can just go 1111. You can just fill that in up here. And so 1111 is actually 15, right? So just use the tool that they have given you. If you have a different number, 1000, 1000, you can change these back. 1000, 1000, you get 136. Right? And so you don't have to do exactly what I did. You can just use this tool to help you here. Now, when they say convert the number 17 to an 8-bit binary number, this is a bit trickier. You could just kind of do it with trial and error. Of course, you can click show your answer, but kind of what you could do is, how can you make a 17? Well, look at the numbers here, 128, 64, 32, 16, 8, etc. What you can do is you can just say, well, how do you get a 17 out of these numbers? Well, you start with the biggest one that's you can get. So the biggest one that's smaller than 17. So 16. So obviously, if you click in there, you get 16. But then we need 17. So we need one more. So go over to the 1 and click at that. And that's 17. And so the binary number is 0001, 0001. That's 17. So 0001, 0001. Now there is like a method to do this without this little calculator. I think I'm not going to show it in this video because I think I do want to have like an iPad or something I can draw on to show you it. But all right, let's do the last one. Convert the number 51 to an 8-bit binary number. So same idea. Like if you're trying to get to 51, you don't click on 128, right? Because that's already too big. You don't click on 64 because that's already too big. But if you're trying to get to 51, well, we probably need a 32, right? So now we got 32. And maybe we need a 16. So click on it, 48. Okay, we're up to 48, which is smaller than 51 still. So how much more do we need? We're at 48. We need three more. We just need three more. So at that point, you can just look up here and say we need three. How do you get a three? Well, we can use a two and a one. Okay, so this is our number 0011 0011. Now, why are these all repeating 0011 0011 and like 001 001? Why do they do that? That's just the specific numbers that they picked. Okay, so don't stress. Um, and I guess that's the entire thing there. Okay, so again, I can show you more about binary numbers, how to convert back and forth, but this is really as far as this section wants to go. So I think that's going to be good for now. Um, in the next video, what we'll talk about are the characters. We're not going to do it right now. I'm just opening it for, I don't know why. But a character is just one symbol on the keyboard. So letters, yes, but also like a dash, that's a character on the keyboard. Triangle bracket, that's a character on the keyboard. That's just an O. That's a character on the keyboard. Um, Lots of things are characters, right? Like asterisks are, slashes are, anything is a character. So we'll talk about that next time about how these work, how you declare them and stuff, what we can do with them. Um, but that's it for now. So I'll talk to you later.